So welcome to today's lecture, the second one in satisfiability checking this semester. So the last time we had a kind of overview motivated why it is important to look at logic, formal logic, and we looked short which logic we will deal with this semester, and today we start with the first one. This is propositional logic, and probably today what I will tell is nothing new for you, perhaps some new sides of viewing the semantics of propositional logic. But you can just relax. This will not be hard to follow today. So some of the slides are from the website of the Decision Procedures book, which is partly the basic of this lecture. This book, the Decision Procedure book, is available in the Computer Science Library. Hello. In some, I think 10 books are there. So if you do not want to buy it, then you can also use it there. Not all contents are in this book, but a part. We go a bit deeper than in the book. So, as you know, we talked about last time already, logic is specified by syntax and semantics. So if you talk about propositional logic, then we will first look at the abstract syntax, then at the semantics, and then we will check, formalize what it means that formulas are satisfiable or valid. We will look at some examples why propositional logic is good for modeling. So how can I model different problems with it? And later, if we have also decision procedures, then we can solve these problems. After they are modeled, we can check them automatically. Then for the later sections or later parts, contents of the lecture, it is important to know some normal forms. And what we will not look deeper in this semester but mention it today is deduction. It's a kind of proof systems for different systems, and we will look here at the proposition logic. Okay, now let us start with syntax of proposition logic. Probably you know how we formalize abstract syntax. We write something. This is a typical element for a formula. This is the sign for I define it to be, and now the grammar. What are propositional logic formulas? Nobody?
A for atomic propositions.
Yeah, so we have oft atomic propositions or?
Or phi and phi. Or not phi.
Exactly. So I have conjunction and negation. This syntax is called abstract. Why I use just these typical names. So if it is not abstract, then I write phi1 and phi2. If it is abstract, then I just use the type. That's why it is called abstract syntax. Okay, and for that we need a set of atomic propositions, which we will denote by prop. These are just Boolean variables. And we will write prop formula for the set of all propositional logic formulas. Now, what are these propositions? I mean, how can I use this logic later? If I model a problem, what is this set of atomic propositions good for? These are just Boolean variables. So actually it is funless. So I take a set of variables which can be 0 or 1, and I write a formula with them. They have a kind of stronger meaning as 0, 1, normally in modeling. Okay, if these are variables in a circuit, like if in a certain part of a circuit there is electricity or not, or there is, what is Spannung of English? Voltage or not, then this is actually can be 0 or 1, but even then they encode some more complex statement, namely if the voltage is above 5 volts, for example. And the same way you can use these atomic propositions to encode more complex statements, like the value of x is larger or equals 0. This can be an atomic proposition. If it is true, then its value is 1. If it is not true, its value is 0. And then you bring in the truth value of these models, of these statements into your model by labeling. Perhaps you know already cryptographic structures. You have some systems. Let's say, for example, this, a set of states. In this case, I have 3 states and transitions between them. And now what do you do to describe properties of these systems? Since this is already abstract, normally this model is, let's say, a state space of a program. Yeah? But since everything is abstracted away, you don't have the variable values anymore. So what do? In order to have a simple model, but nevertheless be able to state properties of that, you just label the states. For example, you can put on this state, you can say, in this state, x is less or equals 0, and y equals 2. And now, these are just strings, because you already assured that they hold. So this, instead of s less or equals 0, I can also write a, and instead of this, I can write b. Hello. And now I have an atomic proposition set AB. Everything is hidden. The states, what is inside is hidden. It is hidden what is behind the proposition. But what I know is the correspondence. Which proposition is satisfied in which state? So this is the basic idea of why propositional logic is used so frequently in computer science. Because the systems are more complex, but it is always abstracted and reduced during the modeling process, such that at the end you can talk about more complex properties than binary properties. So this set of propositions now assume for the moment that it is just a set of Boolean variables, but keep in mind that they are more expressive, actually, together with the modeling. Okay, then we have some more operators that we use in propositional logic. All are syntactic sugar. Actually, here now we have negation and conjunction. This would be sufficient to use one single operator. With one single operator, binary operator, I can express everything else. And I think you will have an exercise to this question. Syntactic sugar for the other operators. Which other terms do you know in propositional logic? Besides propositions, negation, and conjunction? Like one, we also say true. How can we define it? Not phi and not phi. Okay, and we can reduce it to atomic propositions with sufficient A and not A. If A is an atomic proposition. Exactly. This is true, and what would be false? The other? Okay. You can do that, but you can also define false as A and not A, and true as A or not A. Actually, it's the same. If you put a negation and pull in the negation, then you get the same.
Also, we have no or here.
Oh, okay. So how do we define or?
Not phi or not phi.
Or? Not? Not phi?
And not another subformula. And then of psi.
Not psi?
And then the gate around it.
Okay, and this is, so we have negation, and then we have disjunction, and then we can use this here. What else? Implications? Exactly. Now we have or, so we can say not phi or psi, but else? What is used frequently?
Equivalent. So phi1 implies phi2 and phi2 implies phi1.
Exactly. Implication back and forth and back. And perhaps one last operator which is frequently used is XOR. How can you define XOR? Binary?
And not phi1 is equivalent to phi2.
Exactly. Yeah. These are the mostly used. Of course, you can define more. Now we know how to build proposition logic formulas. And the next, okay, some examples. They must be well formed, especially if I go back. Here we have some parentheses over around the terms. Why, actually? Why can I let them away? What happens if I let it away? Exactly. So, and then that's what you usually do. We define the precedence that not binds the strongest, then and, or implies and if and only if is the usual one. And then if I let away the parentheses, then in this case nothing changes. In this case, actually also not, because the unary is implied inside out. In this case, also nothing changes because the and is associative. And in the implication, this would be also fine. Can you tell me an example which changes its meaning if I remove the parentheses? Just an example with parentheses, and if I remove them, then it gets a different meaning. Okay. This is an extreme example because if I remove the parentheses, then the not is applied to quite different operators. Another example would be a and, B or C. That means that in the parentheses is something scoped which is weaker, does not bind so strong than the other outer operator. So if I remove it, then actually these two will be applied first. So we still need the parentheses, but where it is possible, we will remove them. So in some cases, I can remove them, and in some cases, I must keep them. Okay. Now we have syntax, and we would like to know what is the meaning of propositional logic formulas. So we look at the semantic. As the first order logic theory, later we look also at first order logic, and we will put propositional logic into the context of first order logic as a certain theory. And those of you who still remember what is a first order logic theory and what is its meaning. First we need the domain. And of course, since we said that we have Boolean variables, the propositions, we have the Boolean domain of 0 or 1, 0 and 1, or true or false, or bottom and top. Then we have an interpretation which assigns values to our variables from their domain. In general first order logic, you have also functions symbols, for example, or predicates, which will get a meaning. Now we don't have anything like that. That's why our interpretation is quite trivial. It's just a function assigning values, Boolean values to Boolean variables. And since these interpretations are of special form, we call them assignments and use V to denote the set of all assignments. So, what are these assignments? For example, if you have a propositional set AB, then such an assignment assigns values to A and B. And the following, let's assume the value of A is 0 and the value of B is 1. So we can look at this interpretation as a function. Just to see some other possibilities, we can also see an assignment as a set of variables. These are just Booleans, so it is a kind of, I select a set of variables which are true. So I could also look at an assignment as a set of variables, defining true for them and defining false for all the other variables. If we look at our previous assignment alpha, this would contain just this variable b in the set because only the value of b is true. And the third view of an assignment is just a bit vector. That means if I have an order on the variables, this is important because otherwise I do not know which bit corresponds to which variable's value. So I have an order on the variables, then I can just take an assignment as a bit vector, assigning 0 or 1, or defining a 0 and 1 for the ith at the ith place for the ith variable. And probably you have seen all three types of this already now. These are duals. So you can just choose if you define something which one you use, and we will use as a function. Okay, now we have a domain, and one more thing that we should make clear is the set of atomic propositions. Actually, it can be infinite. So if you build a model, then you can just take some new atomic propositions. In order to restrict it to a finite domain, it is important to see that each formula that we consider is finite. That means it can also contain only a finite set of atomic propositions. So if we look at this projection, it's given a formula phi, and we denote by AP of phi the atomic propositions that indeed appear on phi, and this is a subset of all propositions. Then if we have an assignment, or if we have two assignments, alpha 1 and alpha 2, if they agree on the values of those variables which appear in my formula, then of course the formula evaluates to the same value under both assignments. So this way we can make the functions finite, even if the atomic proposition set is infinite. Okay, and in the following, for simplicity, we will just assume that they are both the same, but we have in mind that it is not quite true, because we do not always want to make this projection. Okay. So we will look at different semantics. Of course, they are similar. And today we look only at some semantics. We will look next week at SAT solving, and this is quite different from these methods of evaluating functions, because that is algorithmic. These are more, we will look at these different kinds, and we will take a kind of mixture of them in SAT solving. So first, truth tables. We will not make use of this, basically, but this is the one you probably already got known, as you got known to propositional logic. So what are truth tables? It defines the semantic of the operators in the basic case. So it is given truth tables for not and end. And then I can derive from these truth tables for all possible propositional logic formulas. How do I do this? First, here, these two are the basic ones, and the other ones are syntactic sugar. So the truth tables look like, hello. You have one column for each variable, each proposition appearing in the formula, and you have one column for the operator that you just considered. And depending on the number of variables, if it is a binary operator, that you have, of course, 2 operators, so you have 4 possible combinations of values. And for each possible assignment, you have a row. And in this column, basically, we define now what it means that applying the negation, a unary operator. Note that, of course, you can check that this is true. But even if you would say it is not true, this is a definition, because this is the basic case. Yeah, so it is out of question. If P is 0, then the negation is 1. If P is 1, then the negation of 0. And by the conjunction also, as you would expect, only if both values are true, then is the conjunction true. And in all the other cases, it is false. And with this part, we are done with the definition of the semantics. And then all the others I can derive. For example, if I have P or Q, then I can take the syntactic definition of the disjunction and apply recursively the negation and conjunction to get the truth table for the disjunction. If I don't want to do that, if I allow this syntactic sugar also per definition, then I can derive it, and then I can give it also in the table, that I do not have to compute it over and over again. So it is easier to have them also as truth tables. Now I have all basic operators, and what happens if I want to compute, for example, I think there is an, okay, that I already told. So each possible assignment corresponds by a line. And if I want to have the value of a formula, then I look at that column. And for example, if I want to have P or P and Q, how do I derive it? Its meaning for the different assignments. So all up till now, the operators are given. Yeah, all this part is given. And now I would like to fill in this. How do I do this? Hmm? Exactly. So here. And then?
Right down, right. And then we evaluate P or the content on the output.
Exactly. So P and Q are just right here in the size is 0, 0, 0, 1. And P is 0, 0, 1, 1. And now in the disjunction here, I must look up these rows. So 0, 0 is the first row. So the disjunction is 0. Here again the same. Then I must look up 1, 0 in the disjunction. 1, 0 is the third row. And the result is 1. And then I have to look up the evaluation of disjunction for 1, 1. This is the last row. Here's the result. It is also 1. So now I derived the truth table for this formula. And then I can, inside out, I can recursively define the truth values of each propositional logic formula. So now I had here unary and binary operators. How many binary operators can we define that have different semantics? Now we introduce here negation, conjunction, negation is unary. Conjunction, disjunction, implication, if and only if XOR. And we see that their semantics is different because where do we see that they have different meaning? Yeah, the columns differ in at least one entry. So how many binary operators can we define that have different semantics? Yeah, so 16. Okay, but we do not define them here. Instead of, we look at an example. Okay, we already did an example, but we can look also in this. A or B implies C. Then I have 3 variables instead of 2, and so I have 2 to the 3, 8 rows for the assignment. Then I evaluate first the inner formula B implies C. For that, we had here already this table, so I just take this column. And then A or B implies C, I just took the row 0, 1 in the disjunction, and then I get 1, and so on. Okay, this was the first semantics. Now we look at the second one, and this is the satisfaction relation. This is a functional view of, or relational view of the same satisfaction that we defined with the truth table. So probably you also know this sign for the satisfaction relation, satisfies. And this is a relation between a valuation and a propositional logic formula in this case. So normally we should write this because it is a relation. Valuation, assignment, and the formula are in the relation. Instead of, we usually write this. Alpha satisfies phi. Or we also say that phi holds for alpha, or alpha is a model for phi. Probably all 3 you've already heard. And now how is this satisfaction relation defined? If you should define a relation, what is a relation? Yeah, just a subset of. Yeah? Yeah. So we should define when a pair of valuation and propositional logic formula is in the satisfaction relation. How would you do this if you should write such a definition? That is already a help. It should be defined recursively. If you have an abstract syntax, then nearly every definition which goes over this syntactical object is recursive. That means inside out. It is built recursively according to the structure of the grammar. So in the grammar you have some atomic parts, and you have some parts which you compose from already built parts. So what are these atomic cases by propositional formulas? Which are the most simple propositional logic formulas? Okay, so one, do I define that that an assignment alpha satisfies a proposition? Yeah. Oops. And that means if? Exactly. So for atomic propositions, the assignment directly assigns a value. So what are the next cases in the grammar? Negation. So one is an assignment, is a model for not phi. How can I define it functionally, recursively? Exactly. Alpha is not a model of phi. Then the next operator that we need is conjunction.
Alpha satisfies by 1 and alpha satisfies by 2.
Exactly. Basically, we are done because these are the basic cases. The rest is syntactic sugar. But in order to be a bit more convenient, we can define it also for the other cases. So what would be a disjunction? The meaning of a disjunction.
Alpha satisfies by 1 or alpha satisfies by 2.
Then we have implication. Just somebody.
Alpha doesn't satisfy by 1 or does satisfy
Or we can also say implies, but that's true by the definition of the implication operator. And we have if and only if this is the same. Alpha is a model for phi 1 if and only if it is a model for phi 2. Okay, and now if I want to evaluate a formula, let's say A or B implies C, what do? No, yeah, I have to apply recursively this definition. Assume we evaluate it in the context of an assignment alpha, assigning false to A and B and true to C. And we want to know if alpha satisfies C. What do? Yeah, I want to know if this holds. Then I recursively apply the definition first for the disjunction, then for this implication. Then I have here atomic proposition, which I can evaluate directly in the assignment. So 0 implies 1. Then we know that this is true. So I have 0 or 1, and by the definition of or, it is 1. Okay, this is a bit similar to truth tables, in that in the truth tables we also had this recursion. I use or the existing truth tables to compute the values of more complex formulas. That is what I said, that this recursion, never mind what you do, this recursion will be always in the definitions or in the objects, because otherwise you cannot handle the recursive building of formulas. Okay, this was semantics 2. And now the semantics 3 is the algorithmic view. This is quite similar to the satisfaction relation, but now we do it algorithmically. That means we do not define a function, but an algorithm. So we define an algorithm using the satisfaction relation to answer the problem whether an assignment alpha, assigning values to the atomic propositions, is a model of a propositional logic formula phi with variables from A to P. Okay, how would we do this? If you would get the exercise to write a program that computes the truth value of a formula under an assignment. That means write a program means formulate an algorithm. What would you do? And that means you write a program. First you have to write, depending on the programming language, a function or method or something like that. Which parameters would it have? Yeah, you have a formula and model as parameters. Okay, and then you have to define now the body. What does this method do? Hello.
Because it's a function again, so breaking up the formula into the topmost operator, and you the recursive call on the operand.
Exactly. So it is just make a case distinction on the type of the formula. So if it is an atomic proposition, then you can directly return the value. If it is a negation, then you evaluate the formula and return the negated value. If it is a, let's say, conjunction, then you compute the values of the two operands and return the conjunction of them, the end. If it is another operator, this means the semantic of the operators. That means if here you have the operator conjunction, then here you have and. If it is disjunction, here you have or. If it is implication, here you have implies, and so on. Okay, so now we have an algorithm. We have 3 different semantics to evaluate the function. What is the complexity of this algorithm? Yeah, nearly linear. The operators can have, it can be unibinary, or perhaps it could even be a higher number of, so you branch on the operators. And that's why it is not only linear, but so you have to do the call for each operand. Yeah, and if it is a binary operator, then for each operand you have one branch. So it is not linear, but if you would have only unary operators, then it would be linear. And if you have binary operators, then it is now we have not so much choices left. No? Now how many calls do I make? Let's say I have n binary operator in my formula. How many calls do I do? Yeah, kind of upper bound. If I have one binary operator, that means my formula phi is A and B, let's say. How many calls do I do? Okay, 3. First for the total formula, and then for the subformulas. And then it terminates for the subformulas because they are atomic propositions. Now if I have one nesting, that means I have 2 conjunctions in my formula. Let's say, okay, this is the first call. Then I have 2 further calls for this operand and for this operand. Then this is a conjunction, so I will have a call for phi 2 and phi 3. So 1 call, 2 calls, 3 calls, 4, 5. So for n binary operators, I would have how many? Yeah.
So actually it's linear in the length of the formula.
Yeah, in the moment I think also that this is the case, but actually I thought it would be polynomial. I mean, okay, polynomial is not wrong, yeah. Yeah. Okay, so it is probably linear, but especially polynomial. Now the question, if we have here a linear algorithm, why is the problem so hard? So why do we continue dealing with satisfiability checking for proposition logic if this algorithm is already linear? Where is the problem?
If we don't have the model, so we want to find it, so
Yeah.
we want to find whether one exists.
Exactly. So I can only check if one assignment is a model for my formula. But if I have only the formula and want to check if it is satisfiable, then what is the complexity of that using a recursive call of this algorithm? How many assignments do I have for formula with n variables? So the complexity of calling this algorithm on each possible evaluation would be exponential, and this is what is not good. So the exponential we cannot umgehen. So in the worst case it is exponential because the problem of SAT solving is NP hard. So in worst case we have to basically look at each single assignment. But in practice there are methods to do it more smart, especially where the formulas have a certain structure. So I don't want to go in because it is not the topic of today, but it is a quite difference if you have a propositional logic formula which is generated randomly, then as if you have a propositional logic formula which describes the properties of some systems, because they have a structure and they have perhaps some symmetries and they have some variables which are relevant for satisfaction and some which are not. So in worst case, it is exponential, but for a lot of practical cases, you can do it better. Okay, so we already made an example, but here's another example for the evaluation function application. Now I have here a disjunction, A or B implies C. So first I call the evaluation function recursively to the first operand A and to the second operand the implication. Then, of course, in order to evaluate the second one, I will have to call it recursively again on the operands B and C and check if the first one implies the second one. And the first one, A alpha, evaluated already to 0. Now, since here I have, again, atomic propositions, I can evaluate it, the formula finally also to 1. So it is a good sign that all three semantics give the same value to our formula. And now we know that this formula is satisfiable, especially alpha is a model for it. Good. Now, we define the satisfaction relation in different forms semantically for what it means that an assignment is a model for a formula. We can generalize it a bit. I don't know if you already have thought about it, but the formula itself specifies a set of truth assignments, namely those which are models for it. So this is a dual view to look the formula as a set of assignments which satisfy it. And then you can also extend the satisfaction relation to sets of assignments. So, for example, you can define the models of a formula like the set of satisfying assignments. And the recursive definition is, again, we give now only one semantics. The models of A is the set of all assignments for which this formula is true. Then recursively, the next operator would be the negation. What are the models of not phi 1? The set of assignments that satisfy not phi 1, how can you define it recursively if you know the set of assignments for phi 1 that are models? Yeah. So I take all assignments without the models of phi 1. This should be that satisfy not phi 1. What is about conjunction? Again, it is a recursive definition. That means assume that I know already the model set for phi 1 and phi 2. What is then the model set for the conjunction? Now it is not so complicated. Yeah, it is just the intersection. Okay, and for disjunction, the union, implication, sometimes I don't know if the question is too easy to answer. So how can you define, if you know the models for phi 1 and phi 2, how can you define the models of phi 1 implies phi 2? Exactly. So either phi 1 is not satisfied or phi 2 holds. This is the usual definition of implication. Good. An example. If you want to have the models of A or B, then basically it is defined to be the set of those where both are satisfied. And this is compatible with our recursive definition we just gave. So if I want to build the models of A or B, then these are models of A union the models of B. That means those valuations which, for which A is true, union those valuations for which B is true, and then I can directly to this set. Okay, now we see formulas also as models. And for a formula and the valuation, this is equivalent that either the valuation or the assignment satisfy the formula or it is in the models of the formula. These are just syntactically two different ways of telling the same thing. Okay, and now we can extend also the satisfaction relation. Until now, what we knew, what we had is the satisfaction relation between an assignment and a formula. That means what we said is alpha is a model of the formula phi. Now I can extend it also to sets of valuations. I can say that a set of valuations is a model for phi if each valuation in this set is a model. That means the set is a subset of the models of phi. This is just a convenience notation. And we can also define the same thing to formulas. I can also define that one formula is a model of the other. What can it mean? Now, yeah, if all models of phi 1 are also models of phi 2, because this formula, we said, can also be seen as a set of assignments. It's models. So it is a set of models, and this was on the previous slide, that this satisfaction relation holds if each element in this model set is a model of phi 2. That means, for example, this one, x1 and x2 is a model of x1 or x2. Does it hold? Yeah, because the conjunction, when the conjunction is true, then you know that the disjunction is also true. Is the other way around also true? Of course not. Can you tell me one assignment which is a model of x1 or x2 but not?
x1 to 1, x2 to 0.
So the bit vector 1, 0 or a function assigning true to x1 and false to x2 is a model of this, but is not a model of this. Good. Now we had enough formalities for syntax and semantics of propositional logic. So just conclude. We have a syntax, we have propositions, negation, and conjunction. We can define syntactic sugar like disjunction, implication, and so on. For the semantics, we looked at different semantics, but what we keep in the conclusion is that the basic of the semantics are assignments. You can see them as functions, assigning to each proposition a Boolean value. You can see them also as sets of propositions or as bit vectors. Usually we do the function view. Then for the satisfaction relation, we have seen the three different semantics. And the third one is the functional one, which we will make use of most often. This is the models relation. And this can be defined for pairs of assignments and formulas. That means, for example, alpha is a model of phi. We can define it for sets of formulas. For example, this assignment set is a model of phi if and only if all assignments in this set are models. And I can even define the satisfaction relation between formulas. Phi 1 is a model of phi 2 if all models of phi 1 are also models of phi 2. And I can also define the model set of a formula. Okay. Do you have questions to this part? Okay, this was not so hard for, I don't know, may I ask how many SSE students are there? 5. How many bachelor? Okay, master. Are there any diploma? Okay. So for those, I don't think that you have problems with that, but we will put into the L2P some examples for propositional logic formulas, syntax semantics, and evaluation. So if you like, then look at them. I do not do this in the lecture. Then there is last thing we must define is satisfiability and validity, because finally this is the question that we pose in this lecture. So what does it mean that the formula is valid? A formula is called valid if each assignment is a model of it. That means the truth value is independent of the values of the variables. Can you tell me a valid formula or a tautology? Yeah, A or not A. Actually, this is how we defined true. Independently of the assignment of the value to A, this is true. Okay, and what is satisfiability? When do we say that the formula is satisfiable? Exactly. There exists a model that satisfies it. That means the model set is not empty. Now, what is the relation between validity and satisfiability?
The formula is a tautology if the negation formula is not satisfiable.
Exactly. So phi is a tautology if and only if not phi is not satisfiable. That means especially that if I can check satisfiability, then I can also check tautology. And if I can check tautology, then I can also check satisfiability. So it is sufficient to deal with one of those questions. Also, we have some more notions like unsatisfiability. It is a formula is unsatisfiable, its model set is empty. Also this I can derive from the other two. So it is really sufficient to check one of them, and then I can decide also the others of them. Perhaps we look at this picture. So if we look at the whole set of formulas, then we have some of them which are unsatisfiable, they do not have any model. Then we have some which are satisfiable, they have at least one model, and the subset of satisfiable is valid, where all assignments are models of the formula. Okay, and I said it is sufficient to check one thing. Let's say, for example, validity, and then I can decide the other one. So I can, or let's say if we can decide this model relation, then is it sufficient? So if I give an algorithm, let's say for satisfiability, how can I derive the other things? Validity and unsatisfiability, or satisfiability. So if I can decide if something is valid, then what does mean if the answer is false? That means phi is not valid. What is then phi? What kind of formula? Yeah, it is not valid. That means it is either satisfiable or unsatisfiable, but there at least one assignment will not satisfy it. And what does this mean? Not phi is not a tautology. Yeah, if not phi is not a tautology, that means not phi has at least one violating assignment, so phi has at least one satisfying assignment. And what is this? What does it mean for phi? Yeah, so if not phi is a tautology, that means every assignment is a model of not phi. That means phi cannot have any models because the models of phi is the set of all assignments minus the models of not phi. Okay, examples. What is this formula? Satisfiable, unsatisfiable, or tautology? It's a tautology. Of course, if both bits are true, then at least one of the bits are also true. What is about this one? X1 or X2 implies that X1 holds. Exactly. Can you tell a satisfying assignment? Mm-hmm. Yeah, so if X1 is 1, then it is satisfied in each case. And can you tell an unsatisfiable assignment? Exactly. So if this is true, that means X2 is true, but this is false. Then it is not satisfied. So it is satisfiable, but not a tautology. What about this one? X1 and X2 and not X1. Is it satisfiable? Yeah, so X1 and X2 holds, and not X1 holds also. Can you give an assignment that satisfies this formula? No. Okay. No, the answer is no. You cannot give any, so it is unsatisfiable. Yeah? Then we have some more valid formulas which you already know and have used. So A and 1 is if and only if A. So you can remove conjunction with true. You can remove also conjunction with 0 because it results in false. Then you can also remove double negation. This is already what you use steadily in mathematics or in arguing. Do you know some other tautologies which you frequently use?
Maybe A and A is similar to A.
Yeah, that's also good. So here by the simplification, A and A, if and only if A. Some others? For example, distribution. So if A and B or C holds and you want to have it in disjunctive normal form instead of conjunctive one, then what do? Now you make use of the distributivity and you say this is if and only if A and B or A and C. And also the De Morgan rules, you apply probably the negation. If you pull in the negation or pull out the negation in a formula. That means not A and B is if and only if not A or not B. And similarly for disjunction. So these are tautologies, and that's why they are kind of axioms. Yeah, they are not axioms, but you can derive them from axioms to be valid. And that's why you can use them always. You can instantiate these rules with different variables. So if this rule holds here, then instead of A and B, you can put in X and Y. It holds, of course, up to renaming for all possible variable names, and it holds for all valuations. So you can use them for equivalent transformation, the tautologies. So that's why tautologies are important. And for example, if you can do satisfiability checking, then you can prove that something is a tautology. You can prove it also by usually the usual way for proving mathematically tautologies is derive them, but you can the way how you derive them, it doesn't matter. So you can also do satisfiability checking, and if they are tautologies, then you can use them. So we need algorithms that firstly are decision procedures for propositional logic. That means that they give a correct answer to the satisfiability problem. And another, this correct answer is correctness or soundness. This is called soundness. And it should, and it should always terminate. What is that for algorithms? If they always terminate, then they are complete. That means for each, to give an answer for each, to each problem in finite time. This is completeness, and correctness or soundness is that all answers are correct. All answers are true. Okay, so what we want to have, now first for proposition logic and then later also for different logics, is a satisfiability checker, a solver is usually called. You put in a formula phi, and you would like to get the answer if the formula is unsatisfiable or satisfiable. And we know, we talked about it already, that by having a solver for satisfiability checking, we also have a solver for validity checking, because we know that the formula is valid if and only if the negation is unsatisfiable. So if my solver gives the answer no for this formula. Okay. Do you have questions until now? No. Then we look today, the last thing is we look at some examples for modeling with propositional logic. So what is this logic good for before we go further with the stat solving? And we will look at 3 examples. The first example is, these are, I forgot the slide. So there are different problems in the industry that are used, that are solved with propositional logic satisfiability checking. Perhaps the most prominent one is chips and circuits. It is extremely expensive if you have bug in hardware. The later the design stage or the selling stage, the more expensive it is if you recognize that there is a bug, which is crucial. And with crucial means it influences the correctness of your system. If it happens in the early design phase, then it is relatively cheap. Because you can imagine that you have this design process. You have first some planning stage, then you have some early design stage where you make specifications, then you have some refinement, then some implementation, then you have some production line, then you have selling, and so on. This model is called the waterfall model because this is like a waterfall, but you can always go back. If you recognize that something is not good, you have an inconsistency in your specification, or you have some bugs in your system, then you can always go back. Actually, depending on what you detected, what kind of problem you detected, you go back either only one stage. You can also go back several stages. So from each stage, actually, you can go back to each other stage. And the later you recognize the bug, the more you have to redo. Especially now also, who was it, Toyota, who called back I don't know how many cars because they have some bug in the electrics, in the doors. And in the cars today, there are hundreds of chips, and the most complicated problem is how they interact. Chips are digital. So actually such problems you can formulate in propositional logic, and then you can at least do bug hunting Verification is a bit more complicated because the systems are very large. So doing bug hunting until you reach some diameter that you know if you didn't find any bugs until then your system is correct is very time expensive. But what you can do is really bug hunting and thereby saving money, because if you can already check your model and find the problem at an earlier stage, then you do not have to call back your items, but you can already correct it at the design phase. And it is really in the industry for hardware, SAT solving is a standard method for testing and verification. But of course you use it also in other fields, in logistics and planning, also in artificial intelligence, in cryptography. And today we will look at three simple problems, three everyday problems. Like you have a family and this family has a wedding and they have to plan the wedding guests, and these persons have some constraints on where they are willing to sit. Especially these three persons, the aunt, the sister, and the father are a bit conflicting, and they have the constraints that the aunt doesn't want to sit near the father. The aunt also doesn't want to sit in the left chair, and the sister doesn't want to sit to the right of father. So now the question is, can we manage to satisfy all of these constraints and make a placement for the wedding? Or do we have to skip the wedding? Or so of course we can also think about it. This is you can find such combinator problems as puzzles or as in the internet. It is also fun to think about it, but we want to do it now differently. We want to formalize it as a propositional logic formula and then apply a SAT solver to check this formula for satisfiability. So let us try to formalize. Okay, did anybody find out if it is satisfiable? Not satisfiable. So the aunt, we have three places, yeah, three chairs. Let's say chair 1, chair 2, chair 3. And let's say this is the left one. So aunt doesn't want to sit in the left chair. That means we have here only father or sister. Then the aunt doesn't want to sit near father. That means the aunt, the sister always has to sit beside the two. Yeah. Yeah, this is the only way of not sitting beside the father. Oops. So that means the father has to sit here. Yeah. But the sister didn't want to sit to the right of father, so there's a problem. Okay. But now we encode the three persons, aunt with 1, sister with 2, and father with 3. And we also introduce some propositional variables. Now we have to make a decision. So I proposed here that we introduce a propositional variable for each pair of person and place. That means for statements like father sits in chair 1, or in the left chair, or sister sits in the middle chair. For each of such combinations, I introduce a propositional variable. Is it a matter of taste? Could I take also another choice? If you want to express the problem in propositional logic. Or is it the only way of doing this? Can also be. So the basic problem is that we have this relation, who sits in which chair. And our logic is not strong enough to have either uninterpreted functions or predicates. Yeah, like in first order logic, you have predicates. I can write something like sits. Sits in person, place. Yeah, it would be sufficient to define such a predicate, but we do not have predicates. We have only propositions. So this relation, who sits in which chair, I cannot express it if I have variables for the chair and variables for the person. I could express it in first order logic, but not in propositional logic. So basically, I don't have much choice. Yeah, that we could also do. But basically, you do the same. Now, yeah, you do not encode who sits where, but you encode the whole row. Yeah. So how could we do this before we go to my solution? So you have 3 persons. For each person, yeah, or you can say you have 3 seats, so you have 3 times 2, 6 possible order. Yeah, you don't have more. 6 possible order. Ah, that's not so much. So we would need for each order probably, so we need 3 bits. Why do we need 3 bits? If I have n values, how many bits do I need to encode it in propositional logic? Let's say the nature numbers 1 to n. If I want to encode it in propositional logic with propositional variables, how many bits do I need? Yeah, log n. Log n propositional variables because on the other way, if I have m propositional variables, then of course I have 2 to the m values. Yeah, so the other way around is log 2n. And now I have 6 seats. So for 6 seats, 6 possible sitting combinations. So I need 3 propositions. Let's say they are called A, B, C. And now I have to say which assignment corresponds to which sitting order. Let's say if they are both 0, then it is Vater, Sister, und. If it is 0, 0, 1, then it is Vater, und, Sister. If it is 0, 1, 0, then it is Sister, Father, und, Sister, und, Father. And then I have 2 left. This is with the und. And then somehow I have to encode in my formula that I take only one of these 6. That means the remaining 2 are not allowed. So I should say that these 2 combinations do not hold, and then I have to encode, I have to check actually here, for example, und doesn't want to sit near Father. Then I have to check already by building the formula where it holds and where not. So und doesn't want to sit beside Father. That means this one doesn't work. This one doesn't work. This one not, and this one not. Due to the second constraint, I would add it. And then und doesn't want to sit in the left chair. Means this one also not. because aunt is in the left chair. And the last one is sister doesn't want to sit to the right of father, but here the sister sits to the right of father, so also this is excluded. So basically by building the propositional logic formula, we already solved the problem. That's why what we do now is that we introduce variables x, I, j, and they mean that person I is cited in place j, where I and j go from 1 to 3. And now we have to use this variable to formalize our constraints. So what do we have to encode? Which statements or properties?
Every person needs place.
Exactly. Every person sits in at least one place. And then?
Every person, and no person sits in more than one place.
Exactly. This is now necessary because we are not related. They are not related. Yeah, if I encode with one bit yes or no, then it could be that x1, so the first person, this variable is true for chair 1 and for chair 2. Yeah, they are not related. So I have to encode that one person cannot sit at the same time in two chairs. Okay, what else do I have to encode? Okay, I have to encode all three constraints. And do we need something else? No, let us think. I think that's all. So let us start with the constraints. O doesn't want to sit near father. How do I encode it? The aunt doesn't want to sit near father. Okay, we look at this first. Let's say aunt is 1, yeah? So the aunt doesn't want to sit near father means if aunt sits on the left or on the right, then the father is not in the middle. Father is 3. If the aunt sits on the left or on the right, then the father doesn't sit in the middle. And the other combination is that the aunt sits in the middle, and then the father sits neither on the left nor on the right. This is a very strong constraint. Okay, what is with aunt doesn't want to sit in the left chair? Aunt is 1, so not x11. And the last constraint is sister doesn't want to sit to the right of father. No, how is the constraint for that? Implies if the sister sits in the middle, then the father doesn't sit in the left, and
x to 3 implies not x 3 to.
Exactly. So if the father sits on the left, that's just the other way around on the slides, but this was also right. So if the father sits on the left, then the sister doesn't sit in the middle, and if the father sits in the middle, then the sister doesn't sit on the right. Now the constraints that you said, each person is placed, means that the first person is either in seat 1 or 2 or 3, the same holds for the second person, and the same holds for the third person. Then each person is, okay, this is just a more complex formalization. Then no person is placed in more than one place, means for each person and for each seat, it is the case that either the person I is not in seat J or the person I is not in seat J plus 1. Not in the other chairs. Okay. And since I do that for all chairs, I only have to go to the right. Very good. So we have 9 variables and 26, yeah?
There one constraint missing, for example, that only one person can sit in one chair. So I still think I can solve it if I say each and every person in the second chair.
Yeah, indeed. Yeah. Yeah, indeed. So I think for each person and for each seat, you have that x1, wait, for each seat and each, so I want to say that one person doesn't, no, in one seat you don't have 2 persons.
Just say that no seat is without it.
Not seated. Yeah, so,
No seat is empty. No seat is empty.
Yeah, that's also good. No seat is empty. Yeah, it is an implicit encoding of the fact that no seat is used twice. And we can, of course, do this. This is indeed the best one. So X either in second person or the third person is sitting in the J. Yeah? But you have to be careful by, so sometimes you want to encode something and then you encode something different which is equivalent. It's okay, but you must be sure that it is equivalent. In this case, I think. Hmm?
But still, that person in one place, for example, if 1J and X2J are true.
Yeah, but if they are both true, so the person 1 and 2 sit at the J's place, then the problem is that you say here that each person is placed. So each person is in one of the chairs. And then you have that no person is placed in more than one place. So each person is at exactly one place. And now what was still missing is that they can take the same chair. So for example, all 3 persons can sit in the left chair. And this is excluded by this, in that we say that in each chair there is one person. That means if I put all 3 in one chair, then one of the other chairs will be empty. Because I said that each person sits in at most, is placed in no more than one place. So at most 1. So each person can be in 1, in at most 1, in at least 1, and no chair is empty. Then it is equivalent to nobody sits in 2 different chairs. No 2 persons sit in one chair. Okay. I think we left the other 2 examples for Monday. And we stop here. So we finish next time the examples. We will look at deduction on Monday. On Monday we will already start with such solving. Okay. I wish you a nice weekend.
Exercise on that. So
just in L2P. There is an extra folder for exercises, and there you can find the exercises. This is voluntary, but it's very necessary to just understand it.
In case somebody has problems with printing, then you can just come, then we can also give you some printed version.
I was waiting, didn't know where can I get the lecture slides?
Everything in the L2P room. So you must register to the lecture, and then you get access to the L2P room.
And we should also do some exercises, as I heard. And where can I get them?
The exercises are also in the L2P room.
It's L2P.